Hello and welcome to this video recapping the entire course. Hopefully, you've managed to stay on till this moment, going through the 10 weeks of lectures on big data. So, the construct of this course is such that we wanted to get the students who take this course introduced to practical aspects of analytics at large scale. Big data turns out to be, like we've looked at the earlier classes, just a tool, right? Or a collection of tools and technologies and concepts which enable you to do the analytics that you need at large scale. And the reason you do the analytics at large scale is because most of the real world systems that you see today are all massive data systems, right? Because that's how the impact is, and that's where the common touch points are for many of the practical services that we use in our daily lives. So I believe we have actually gone ahead and done justice to a lot of the different concepts of big data here. So in this video, we'll recap some of the key concepts, and then towards the end, I'll also touch upon what is actually going to be important for you to be really thorough with, especially from a perspective of the final exam, but also from the point of view of what you might end up using on a daily basis if you choose to pursue a career as an ML engineer or as a data scientist in a big company which has lots of data, or as a data engineer who ends up working with big data pipelines all the time. So we've also gone through the associated aspects of cloud-based technologies, and that was actually quite important for us to become aware of, because big data does not exist in a vacuum. It exists very much as part of cloud-native design principles at the minimum, and even from a practical standpoint, exists in the cloud, especially with public cloud services that make it really easy for engineers like us to build big data pipelines. So understanding cloud was also part and parcel of the learning objectives of this course, and I believe we've actually had a very good understanding of it, not just theoretically, but also with the assignments that have been administered on a weekly basis, where you had to actually log into the cloud and do your assignments on the services there. Okay, so just to recap from the beginning, the notion of big data was something that we spent quite a bit of time on. So this was pertaining to the fact that big data is not just about the 3 V's, which is velocity, variety, and volume, or the 3 V's and 1 C, which is the complexity, but it's much more than that. It's being able to deal with the right type of any type of data at any point in time with any tool of your choice, right? So if you're able to get to that level of flexibility and power, that to me is big data. But nevertheless, we kept coming back to this concept of velocity, variety, and volume throughout the course in various forms, because those were easy to understand concepts. We also look at why is big data really not changing anything materially in terms of the motivation for data science, which is you have to have real world impact. You have to make actions predicated on the models that you produce, the outcomes that you produce from those models. So don't just do data science for experimentation's sake. That's necessary. You might do 10 experiments and you find that 8 of them have failed because they don't produce anything meaningful. But the 2 remaining experiments which are producing something meaningful, you have to take it to the logical point of conclusion, which is making it run in production and producing actions or producing outputs that influence actions. That's what makes it impactful in the real world. Okay, so we then dove deeper into the foundational concept of big data, which was divide and conquer, and how every problem statement that you need to tackle with massive data comes down to how you can break down that bigger problem statement into smaller problems that you execute on a cluster of machines to get local answers, and then you conquer those results with a common process that runs on a single master, or maybe again distribute it back to the workers to get the final answer. So that divide and conquer turns out to be like a fundamental concept across a variety of different things, not just for data engineering or data preparation, but also for machine learning itself, right? And deep learning also, that we saw throughout the course. Uh, then we spent some time comparing what you can do with hashing, what you can do with sorting, and spoke about how the two are equivalent. And that is again a fundamental concept to understand, because every time you find yourself in practice running out of memory, right? Remember that you can choose to implement the same algorithm or the same engineering pipeline with more storage of data on the disk, which uses a sorting mechanism. That way you don't have to be limited by memory. So that's a practical way to look at applying this, understanding that both are doing the same thing. The hashing and sorting of data are producing the same equivalent output. Okay, so then we then moved on to actually looking at the cloud. There are many fundamental concepts in the cloud, but the key is actually cloud native. And we spent some time looking at why cloud native is important and what cloud native comprises of, right? Which is manageability, administering ease, and then observability or traceability. So if you have these three, then your software can be easily put on the cloud, as well as scaled up, as well as applied at cutting edge scale with real time kind of latencies at massive volume, very high velocity, etc., etc. So there is a natural fit between cloud native design and big data. Is one of the things we looked at with an example. Then we looked at the different services available as part of public cloud, namely starting off with infrastructure as a service, which provides virtual machines and hardware. Then platform as a service, which provides ready to use databases or big data execution environments, Spark execution environments, etc., or specifically even serverless for that matter. And then on top of it, we also have this fully vertical stack that we took a look at, which was software as a service, which merges the business application with the data, with the functional part of the software, with the non-functional part of the software, with then the cloud infrastructure itself. All of that is verticalized as a packaged unit which solves a specific problem, which is SaaS. We looked at the pros and cons of each of this, and how, as engineers, you would end up typically using the PaaS version of big data execution environments, because that is the right balance in terms of how much you take on as operational headaches yourself versus how much flexibility you let go when coding up your own pipelines. So in practice, you might find 80 to 90% of your time in real world you spend on PaaS big data platforms, and that's perfectly fine. And if you know that well, that's going to service most of your needs. That's unless you work in developing a platform yourself, in which case you might have to go deeper, right? Infrastructure as a service as well. Okay. Then we started to look at the different types of data. So that was more like a primer on data formats and data organization principles. Not completely, specific to big data, but more generally focused on the origins of data, right? How does a software get designed? And how does a software actually store data internally? The notion of CRUD, right? Create, read, update, delete, operations that happen on the data, and the way the operations are manifested in the source database. All of those play a critical role in the extent to which you can get good quality data from the source system. We spoke about how the files that you might get could be either flat, right, which is like a relational format, no nesting, and or could be hierarchical. Hierarchical is JSON or XML, and in which case you might need to do things like shredding and flattening. Specifically, we spent some time on the CSV format, and that's important to know because in practice, you're going to get a lot of data, which is CSV data, which is easy to visualize as a spreadsheet, rows and columns. But pay attention to the format. CSV is not just one type of format. It's actually a specification which allows for some flexibility in the formats itself. The way the software uses data also pertains to the data model, right? Apart from the way the data has changed. The data model could be like a star schema, which has facts and dimensions. The dimensions themselves could be having versions tracked as part of the table itself, in which case it's called as a slowly changing dimension type 2 or SCD type 2. That's an important concept you have to understand. Then we talked about change data capture, which becomes like a useful tool in case you find yourself dealing with source systems which are old, where the updates to the tables have been happening in place without storing versions, without an SCD type 2. Then we looked at essentially the breakdown of the landscape of data technologies, data storage technologies, I should say. So starting off from OLTP, which is the online transaction processing systems, which is the database behind software applications. Then the other end of the spectrum is OLAP, which is online analytical processing systems, which is where bulk of your time is typically going to get spent. But in practice, keep in mind that in order to create impact in the real world, whatever you do in OLAP, right, using models and data lakes and stuff like that, you have to bring it back into some OLTP application or the other, right? Some software application which is consuming data from an OLTP database. You'll have to plug it into that software in some shape and form. Sorry. Even though these are two different sets of technologies, they are closely intermingled, and you have to understand this. Then we defined what a data lake was, and that's crucial to understand, because there are many definitions of data lakes. It's not clear that one is better than the other, and I'm not saying what I'm proposing is actually the best either, but it's practical, because ultimately the data lake does not exist just to store data, right? It exists to serve needs of the business when it wants to do analytics. So what does a data lake for analytics look like? It looks like a snapshot of all the different sources of data. That in essence is the definition of a data lake. Okay, we looked at, of course, how to create snapshots as well. So that was part and parcel of that week's lecture. Then with that as the background, we started looking at what is the most popular tool or library for big data, which was Spark. But before we got into Spark, we just took a primer on how Spark itself evolved prior to the creation of Spark, right? The foundational technologies as part of Hadoop, and what those technologies were good at, how some of them lived on in the modern big data platform as well. Like for instance, Zookeeper as an example. Yarn is another example. Then we went into Spark. The primer on Spark started off with just giving an overview of the different modules. And that was important to know, because Spark is not just a hammer looking for all kinds of nails to break, or a hammer. But actually you should think of it as a Swiss Army knife or a Swiss Army toolkit. It's got a bunch of different things that you can use at various points in time. So it's got data processing capability using Python or Scala or Java. We focused on Python. That was the PySpark layer, because that's what all of you are familiar with. But you could as well have chosen to do the entire course that we did using Java, right, or Scala for that matter. So that flexibility is great. Then Spark also has SQL capabilities, and we looked at that in great amount of detail in our subsequent week of lectures. So that gives you the ability to go at the same data, not just with procedural programming with Python or functional programming with PySpark, but also with declarative programming with SQL. Then Spark also has Spark streaming. We took a look at, we spent quite a bit of time on that at in a later lecture. And then finally Spark has MLlib. And again, we spent a lot of time on that. So the versatility of Spark and the foundational architecture of Spark that enables it to scale to any volume, velocity, variety of data makes it like one of the most de facto options, right, for big data processing. So we spent a good amount of time, therefore, on Spark architecture itself, the notion of an RDD, the notion of a data frame, the stages, how lazy computations work, right? Lazy evaluations work, the notion of a closure, what gets done in the driver program versus what gets done in the worker program. So that becomes very important for you to understand the performance of a typical Spark program. And then the directed acyclic graph, the DAG, the schedulers. So knowing all of that is important for you to be able to debug what's happening when you start writing mainstream Spark code. Then before going further into the rest of Spark concepts, we spent some time understanding what typically happens before the data science exercise happens, which is basically the data cleansing, feature engineering, data preparation. But those are data science terms, right? But if you look at the classic world of data, they're all at the heart of it, data processing using transformations, right? So we spent quite a bit of time understanding what the fundamental patterns of transformations are, which is ETL. Then those patterns of transformations, they form the basis for you to create a standardized version of data which has good quality. Without those patterns, you might end up doing a lot of custom notebooks and custom data structures or data tables, which not many people can understand, right? Beyond you, if you don't do the right documentation. You might always think that, okay, yeah, I'll get the documentation eventually, it's not a problem. But in practice, we've seen that documentation always suffers. So in which case, instead of relying upon the self-discipline that's required for documentation, why don't you just imbibe yourself with the right patterns of data transformations up front, so that you have a systematic and structured way of producing good quality, cleansed, prepared data that's necessary for data science to take over. That's what we spent a lot of time on in the transformations that we discussed, the patterns, ETL patterns that we discussed. In fact, one of the critical ETL patterns beyond data processing was also the operational angles. And there we spoke about the different notions of time that exists. And that's one of the most common causes of confusion when you start to build real world data science applications. So this notion of a business time, notion of an event time, and the notion of an operational time. So it's important to understand that. And then finally, the distinction between ETL and ELT. So in the world of big data, everything is ELT actually. So that's something we understood the relative differences. And then we spent some time looking at how we round it off all together using a scheduler, right? That connects all these different pieces, that allows you to orchestrate and coordinate amongst these dependencies. In terms of advanced topics, in the context of ETL, we looked at things like late arriving data. We didn't actually spend time like looking at the nuances, but that's one of the most common real world scenarios that you will face. So encourage you to read up about it online in the Spark documentation, which is actually really good about it. Yeah. Okay. So then we looked at the SQL interface for working with data. So before getting specific about Spark SQL, we had a significant amount of time that we spent in just understanding the foundational concepts of SQL, including things like planning, optimizing, executing, etc. How you need to think in terms of joining two data sets together on a common key, The key could be like a primary key, foreign key relationship that you create, that's already there, or a surrogate key that you end up creating, or a reference key that you end up creating. But the fact that these joins happen at large scale make it challenging, right? And can easily make performance go wrong if you're not careful about it. So how do you then get an understanding of what is happening? That's where we started looking at, using explain and analyze statements as, important, tools for you to understand what's happening behind the scenes with the cost-based optimizer. Then the optimizations which are possible with Spark SQL, we spent some time understanding this. And then finally, we rounded off our knowledge of SQL by also looking at NoSQL, where we clarified that NoSQL is not really NoSQL, but it's not only SQL, right? In practice, most of these NoSQL databases actually support SQL-based querying as well. So the 4 types of NoSQL databases are important for you to know. While you might end up using none of them in practice, which is quite possible, but you should know that these varieties of NoSQL databases are existing, so that you can plan the appropriate integrations back from your data science model. Remember the OLAP, OLTP integrations. That's necessary for you to create impact with your data science model. So that usually goes back into some kind of a NoSQL database in the modern software stack. Okay. Then we went on to a very interesting part of big data, which is how do you deal with high velocity data in quick time, which was basically the streaming formulation of the problem of big data. So we looked at the problem of streaming as one of ensuring that the state that's maintained, that's necessary, is always continuously worked upon and moved on, right? The state keeps moving on to the next versions of the state without updating directly in place, and the next state that gets created super fast without doing too many things, right? So which is basically the hot potato principle. So you just keep moving the state, and that becomes foundational as a way to architect streaming systems at large scale, because like we spoke about so many times, anything can fail. And if anything can fail, the last thing you want to do is, spend a lot of time processing something and only to realize that it's failed, and then you have to process again. And therefore you've not made meaningful progress in the small window of time that you have available to you, right? As part of the streaming formulation of the problem statement. So stream processing is super critical for modern age companies, because almost everybody, as consumers like us, we expect our experience with the consumption services to be super fast, very good, like good experience, low latency, not have to wait for like 5 minutes or 10 minutes to get back with answers, etc. So the processing that enables all of this is actually stream processing. So the application semantics for this is something we spent some time looking at. Checkpointing, how do you play back from older data? How do you guarantee at least one semantics, right? And that becomes usually the de facto standard for what you can guarantee. But if you want to take it up a notch and guarantee exactly one semantics, that actually invariably involves way more cost, right? In terms of not just the effort, but also the cost of running software and maintaining state and ensuring that the state is in sync, etc. But it's possible, very much so. It's made easier if you have source software for streaming and destination systems in sync, right? So if you look at it end to end as real time, and you want to control that and make it exactly once, that's possible if all of them cooperate. And there are technologies that do it, right? Like for instance, the combination of Kafka, Spark Streaming, and NoSQL databases. So if you put those 3 together, or Kafka, Spark Streaming, and Kafka, they are actually very good as a trio of technologies that you can layer to get that end-to-end exactly one semantics, right? So that's why these technologies we spend some time understanding in the course. Then we looked at 2 different sets of technologies of stream processing. One native to the Google stack, which is the Google PaaS services of PubSub and Dataflow, and then correspondingly we looked at the open source equivalents of those, which is Kafka and Spark Streaming. So that was what we spent some time on. the Kafka architecture and the Spark streaming architecture, especially the structured streaming, is quite relevant for a variety of different types of streaming applications. So just make sure that you are on top of it and you are able to consciously think about how to layer data as part of Kafka topics and read it using Spark streaming. That is actually going to be a repeat pattern, right, across many of your projects the moment you start to look at applying machine learning models that you create into production, right? The scoring process is usually part of a streaming pipeline. Okay, so then once the streaming sides were done, we looked at the activity of machine learning itself done at large scale, and why that is a challenge in itself, right, as opposed to just conventional machine learning done on a single machine. So here we spent some time understanding the differences between shared memory execution model, which is what typically machine learning on a single machine does, versus shared nothing, truly massively parallel processing, data parallel executions on a cluster like Spark. The cool part here that's worth highlighting again is that many ML algorithms, including deep learning algorithms, are conducive to a divide and conquer style data parallelization, and that becomes the foundation for creating highly scalable versions of algorithms. Then you can just blindly apply that at massive data sets, and for a fact that it will produce the right answer. And Spark MLlib is one such library which has already implemented a variety of these algorithms for you. So we spent some time looking at what the foundational concepts of MLlib are, including the notion of a pipeline, transformers and estimators, and how do you put it all together. Invariably, with all these toolkits, you have also functions that make your life easier, like auto tuners and auto ML concepts. So that's what we also spent some time looking at with an example, and then we kind of rounded it off by looking at in practice what machine learning model building will actually entail beyond just the model algorithm itself, and that was the topic of ML ops. In fact, ML ops has a very long set of discussions that are possible, but we spent some time giving an overview, and that's about it, and then summarize the best practices for how you would end up using ML ops and machine learning at large scale in practice, right? There's a sequence with which you'll practically approach this, and that's a sequence that's worth remembering or storing as a reference, because you'll find that useful as you go through your practical life deploying these concepts in your data science career. And last but not the least, we looked at the challenge of deep learning on big data, and that was special because deep learning itself has completely revolutionized the entire industry of data science, and not just that, right? It's actually changed the world, the way we look at it. Almost every single application or service that we consume as a regular human being, we are touched by AI algorithms which are powered by deep learning networks at the heart of it in some shape and form. Of course, the most popular ones are currently still in vogue, like ChatGPT, Stable Diffusion, Midjourneys, DALL-E, etc. But there are so many more variants and so many more interesting use cases waiting to be found, and maybe you'll be one of them, right? But before you get too further into trying to find a new use case, just understand what could deep learning on larger data sets look like. So we spent some time understanding the training possibilities at large scale and how you have to think about optimizing the resource that's the most expensive, which is basically the GPUs. As part of which we looked at complementary tools to the Spark ecosystem. One such was Horovod. Again, very useful library. Just keep that in the back of your mind. We also looked at briefly ML Flow as part of the MLOps discussion, and that's very useful for deep learning as well. In fact, not just deep learning or machine learning, it's just useful for data engineering in general. And then we also looked at how you can put it all together with an example where hopefully as part of that assignment, you'd have looked at, streaming combined with pre-trained deep learning models, combined with the ability for you to stitch the entire thing as part of an ML pipeline. So that actually kind of rounds off what you might expect in practice, right? So let's maybe take a step back and see where you might actually spend your time on a day-to-day basis if you choose to pursue a career in data science at large scale. First and foremost, you will end up doing a lot of work in data engineering, whether you like it or not, or you might at least have to understand how data engineering happens, right? Even if somebody else does the work for you, because the last thing you want is to be dependent on somebody else to give you good quality data. So best is you understand where data comes from and use that understanding as a position of as a position of strength to advise on the formats in which you want the data, the quality considerations that you want to consider, you want to include as part of the data extraction process, and the set of transformations or engineering that you want to do, you want to take control of, and then get that done, right? And if you do that, if you do these things in a structured way, in a way that's consistent and systematic, then you leave behind a legacy that is worth remembering, right? You leave behind, code bases and documentation, which is actually quite easy for somebody else to follow, and the data becomes the documentation itself, right? The code becomes the documentation, so you don't need to write something specific separately in text. So that's very useful. And then once you do the data preparation steps and you're ready to start doing the model building, then you start to focus on which parts of the machine learning stack are going to be useful for you. Are you going to do it in a single machine at small scale? In which case do you need GPUs or CPUs? Based on the nature of the problem statement, you might choose a classical ML algorithm as opposed to a deep learning algorithm. And if you find out rather that the dataset is too large, doesn't fit in a single machine, you cannot use the multiple cores in a machine for optimization or parallelization. So then you branch out into a cluster of machines, and when you do that, you start to automatically bring to use the big data concepts that you've read. So you start to think in terms of how do I now orchestrate the pipelines? How do I bring rigor to the pipelines that need to execute again and again with different versions over a period of time, as I keep iterating, as I keep changing my model, as the model evolves to meet the changes in the data that's happening, the drift in the data that's happening. So all of that, I put an ML flow, pipeline monitoring as part of ML flow, and then I use version control systems like GitHub to check in my code and ensure that the right piece of code is getting shipped to production at any point in time, and use a feature store to store all of these features that I'm creating, right? The intermediate data mart views that I'm creating for my data science experiments. And then once I'm ready, then I can move from staging to production by just like practically flipping a switch, right? And that flipping a switch is basically just promoting that final code from GitHub into the production environment, and at that time it's ready to be deployed either as a pickle file or a Uber jar or as an API, it doesn't matter, right? And as part of that code, I am also making a decision on whether I'm going to need a streaming formulation for the scoring, or I just need to be able to do it in a batch way. Either which way, I'm ready because I have the principles available with me, and then I can start, producing that code as well and checking it into GitHub and making sure that's getting deployed into production. And last but not the least, I've put enough, observability and thought into, the traceability of the entire pipeline, especially with MLOps and even otherwise in the code, such that if something goes wrong, I can come back and take a look at what's gone wrong, whether it's a functional error or whether it's an error with the pipeline, with the technical pieces themselves, and either which way I'm ready to, repair it again, right? So that's the practical side of how you'll apply all of this in your real life. Now coming to the money end of the spectrum, money end of this lecture, which is how do you plan for your final exam? So what I can tell you is that what we just spoke about as a combination of a bit of data engineering, a bit of model building or model scoring, a bit of streaming. That combination is exactly what you're going to get tested on in the final exam, because that's the combination that's going to be the most common, right, in practice. So that's what we spend. That's what we'll ask you to spend your time on. So as long as you focus on these three things, you should be good to go with it. So great. It was great to share what I think are the concepts which I've learned over these last decade and a half of doing big data and data science. Hope you liked it. It'll be great to receive your feedback. Thanks again. So good luck with the final exam, and hope you're able to clear the degree with full colors. Thank you.